All right, so moving on to our next topic, which is resonance and delocalization. First, some definitions. What the heck is delocalization? That's spreading around of electrons distributing throughout molecules. Resonance itself is the act of delocalizing electrons, and a resonance structure or resonance contributor is a compound that has resonance. In the textbook, Dr. Bruce gives an example of an animal that's used to define resonance. A rhinoceros. She says if you're trying to describe a rhinoceros to someone that has never seen a rhinoceros, you might describe it as it has a horn on its head, kind of like a unicorn, and it has thick, sort of scaly skin, kind of like a dragon. A unicorn does not exist, to most people at least. A unicorn does not exist, and a dragon does not exist outside of Game of Thrones. So why would you describe it as those two things? The unicorn and dragon does not exist, but the rhinoceros that does exist is a combination of some characteristics of a unicorn and characteristics of a dragon. There are some characteristics of each of those non-existent things that contribute to what a rhinoceros really looks like. That's the same way it works in chemistry with molecules. Let's draw some Lewis structures of sodium acetate, CH3CO2Na. That's CH3 COONA. Remember, sodium is a hater. It does not like to make bonds to things, so he's a positive. We're going to make one of these oxygens doubly bonded, and the other one stays singly bonded. The singly bonded oxygen gets a negative charge. I hope you've been practicing your formal charges. So I hope you remember from general chemistry that double bonds and single bonds have different lengths. A double bond is shorter than a single bond. So that might lead you to say this bond is shorter than that bond. It's not. Because of resonance, this molecule could also be drawn as this version, where the oxygen over here is now making a double bond, and the one up there is now making a single bond and has the negative charge. So either one of these are valid, aka this one might be considered the unicorn, this one might be considered the dragon. The rhinoceros, the real molecule, is a combination of these two. The molecule on the left doesn't actually exist precisely as drawn, neither does the one on the right, but there's a combination that does exist. We draw an arrow like this in between resonance structures. That arrow means resonance. It does not mean equilibrium. That arrow means resonance. Organic chemists are really into their arrows. We'll talk about more in a moment. So what does the actual rhinoceros of this thing look like? The actual combination molecule? We would call that the resonance hybrid. And we often draw it like this, with little dot, dot, dot bonds to show delocalized electrons. This is a resonance hybrid. In a resonance hybrid, nobody has a formal negative charge. In this resonance hybrid, nobody has a formal negative charge. There's a partial negative on that oxygen and a partial negative on that oxygen. A resonance hybrid is really a mathematical average of your two resonance contributors in this case, because these two resonance contributors contribute equally. We'll talk more about that. Hold on. So this hybrid is what the molecule really looks like, but rather than drawing tons of hybrids, we often draw lots of resonance structures so that we can see all the little aspects of what it looks like, but we consider in our mind's eye the hybrid, but we don't actually draw very many hybrids in here. So I said organic chemists get really obsessed with their arrows. Another kind of arrow that we draw is curved arrows. Curved arrows show electron movement. So curved arrows can be used to show how one hybrid gets converted, how one contributor gets converted to the other contributor. They look like this. These electrons, because it's electrons that are moving with curved arrows, these electrons can be donated and shared. The butt end of the arrow comes from the electrons. The head goes to the bond. That's telling me I'm going to make a brand new double bond here, this one. But that would make an extra bond to carbon, and carbon cannot make 5 bonds. So I must move electrons from a double bond to become a lone pair up on this top oxygen. So it doesn't really matter where you point the end, whether it's pointed up at the top or over the side, whatever. This oxygen ends up with 3 lone pairs instead of 2 because you broke a pi bond and gave him that lone pair. Curved arrows are, unfortunately, a big deal in this class, and you have to get good at them. But you will. I have faith in you. That was sodium acetate, simple sodium acetate. But there are lots of molecules that have resonance, and we will spend a lot of time drawing resonance and talking about resonance. So it's important that you know the rules of resonance. Here are a few. The real molecule is a hybrid. This is one that I have to continually remind students of all semester. The rhinoceros is what exists. The hybrid is what exists. But the structures that we draw all the time, all of the contributors, are the dragon, the unicorn, the things that don't really exist, but they're giving us a good picture of some of the characteristics of the real molecule. It's very important that all contributors are valid Lewis structures. We can't do things in a resonance contributor that we can't do in a regular Lewis structure. Equivalent contributors contribute equally. We will talk extensively about how to determine if contributors are equal or not. So if we consider the sodium acetate that had 2 main contributors, those contributors I said were equal. So the hybrid can kind of be considered a 50-50 average of those 2. Sometimes there are minor contributors as well, but we're worried about the major contributors right now. More rules of resonance. Only electrons move. And how do you show how those electrons move? Curved arrows, of course. We'll get good at them. Only pi electrons and lone pair electrons move. Do not ever break a sigma bond in a resonance thing. You can only break pi bonds or make new pi bonds, etc. An sp3 carbon cannot accept electrons. You would explode his octet if you tried to give an sp3 carbon more electrons, so be careful. The total number of electrons cannot ever change in a resonance molecule, in a resonance contributor, so be careful there. Let's see some examples of how electrons can move. This says electrons can move from a pi bond to a neighboring position. What does a carbon with a plus mean? This carbon with a plus? It means he's making 3 bonds and has a positive. That means he has less than an octet, because in order to have a +1, he has to have 3 bonds. So less than an octet, that's no good. So we can do a little curved arrow, give that carbon some electrons. Note, the butt of my curved arrow came from the pi bond. The head went to this bond over here. What I'm showing with that is that this rightmost bond is now a double bond. All of the hydrogens stay in the same spots. You cannot move hydrogens in resonance. It's not legit. You can't do that. But I shared electrons over toward to make this new pi bond. The way I think about this kind of movement is like a door swinging on a hinge. This carbon was my hinge. This carbon was my hinge. My door went from closed to open, or open to closed, however you want to see that. It's like a door swinging on a hinge. This carbon had an octet in the beginning. He still has an octet now. This carbon had an octet here, but we took from him. We took electrons away from that carbon, and he's angry about it. And he tells us that he's angry with a positive charge. Remember, carbon's in group 4, minus no lone pairs, 3 bonds. That carbon is a +1. The carbon on the right had not an octet. He only had 6 electrons in the beginning. Now he has an octet. He's satisfied. He's a formal charge of 0. So these are resonance contributors. If I were to draw the hybrid of these guys, that's all the carbons and hydrogens stay the same, but we do a little dot, dot, dot bond where electrons are shared. The carbon on the right gets a partial positive because in this structure over here, he had a legit positive. The carbon on the left also gets a partial positive because in this structure over here, he had a legit positive. So the hybrid is the mathematical average of these two because these are equivalent resonance contributors. Why are they equivalent? Again, we'll see. We'll explain when we have some not equivalent ones in a moment. Electrons can move from an atom to a neighboring position to make a pi bond. This is really implying that lone pairs can move from an atom to a neighboring position to make a pi bond. What has lone pairs? In this molecule, oxygen has lone pairs. And that oxygen is next door to a carbon that has a positive. What does carbon with a positive mean? Carbon with a positive means he does not have a full octet. So we want to give him a full octet, like this. Electrons from my oxygen are being shared now this way. Let's draw it. A 6-membered ring with an oxygen and carbon connected. Hope you've been working on your skeletal structures also. There's now a double bond between carbon and oxygen that wasn't there before. So oxygen had 2 lone pairs, but we took one of those lone pairs to share with the carbon, but 1 lone pair remains. So if I do a formal charge counting for this oxygen, he's in group 6, he's got 2 electrons as a lone pair, and he's making 3 bonds. He's a +1. So that oxygen is now a +1. Carbon, if I look at this carbon is in group 4, and now he's making 4 bonds, so that carbon is neutral. So these 2 resonance contributors are not equal. These non-equivalent resonance contributors do not contribute equally. What that means is the hybrid is not a 50-50 combination of these 2 things. The hybrid is more like one than the other. Maybe you and your facial features and things appear more like your mother than your father, or vice versa. When you have unequivalent contributors, you don't have a 50-50 mixture. The hybrid for this structure would look like this. It would have a partial positive on the carbon and the oxygen, but the hybrid actually looks more like this molecule than the original. Why? How do I know that? Well, there are some priorities to ranking resonance contributors. The number 1 rule to ranking important resonance contributors is the octet rule. What? Yeah, the number 1 rule to ranking resonance contributors is the octet rule. In this molecule on the left, carbon does not have an octet. That's not great. In this molecule on the right, carbon does have an octet, so that's much better. Oxygen has an octet in the beginning. Oxygen still has an octet over here. He's sharing more than he would like, but he does still have an octet. So this molecule, every single atom in this molecule has an octet. Therefore, this molecule is a more important resonance contributor than that one, because no octet right there, remember? So what that means is the hybrid looks more like the right molecule than the left molecule. When we say more important resonance contributor, we mean the hybrid looks more like that one. All right, let's look at another way that electrons can move in resonance. Students often find it difficult to know where to begin when they're drawing resonance. If I see a molecule that has a charge, that is often screaming, help me, help me, help me. Start here is what that is usually telling you to do. It's usually telling you, try to satisfy that charge because charges are not great. We try to avoid charges in Lewis structures if possible. So I'm going to try to start here. I have to first remember that carbon with a minus, what does that actually mean? Carbon is in group 4. He cannot make more than 4 bonds, but this one is being shown as making 3 bonds. In order to have a -1 charge, it must mean that he's got 2 electrons in a lone pair. Carbon with a minus means he has 2 electrons as a lone pair. So if I start with this bottom rule, from an atom to a neighboring position, that's really meaning a lone pair can move from an atom to a neighboring position to make a pi bond. So I'm going to take this lone pair and I'm going to move it over there. That's telling me I'm making a new pi bond, carbon to carbon. But wait, that would cause a problem with this central carbon. That would mean that central carbon has 5 bonds, and that's no good. So we also need to do step 1, which means from a pi bond to a neighboring position. That pi bond can move to the oxygen to become a lone pair on the oxygen. Let's draw this contributor that we just drew, that we just made with our curved arrows. There's now a double bond, carbon to carbon, a single bond, carbon to oxygen. The carbon over here on the left had a negative charge. Does it have a negative charge now? Nope. The carbon in the middle had no charge. Does it still have no charge? Yep. The oxygen up top had 2 lone pairs, even though they weren't explicitly drawn. Remember, you got to know they're there. Those 2 lone pairs are still there, but we've added an additional lone pair on the oxygen. What does that change about the oxygen? He gets a negative charge. Yep. If I consider between these 2 molecules, which molecule is the more important resonance contributor? Remember, my number 1 rule for resonance contributors, figuring out who's most important, is octet. Does everybody on the left molecule have an octet? Yes. Does everybody on the right molecule have an octet? Yes. So by that logic, these are equivalent so far. The number 2 rule, the way I always write it, is negative on electronegative. That's the number 2 rule. After you checked octets and that does not decide it, then you look at charges. You want the negative charges to be on the more electronegative atoms. You want the positive charges to be on the most electropositive atoms. In this, we've got a negative on carbon and a negative on oxygen. Who's more electronegative? Oxygen. So what that means is this one is my winner, winner, chicken dinner. Why is this the winner, winner, chicken dinner? What does it mean to be the winner, winner, chicken dinner? It means this rightmost molecule contributes more to the hybrid than the left molecule. That's what it means. Before we totally move away from this slide, I want to point out one more thing. There is a minor contributor to this molecule where you leave the negative charge in place and you simply move the pi bond. If you move this pi bond, following this purple arrow over here, move this pi bond up to the oxygen, and that's all you do. That makes you an extra lone pair on the oxygen, gives it a negative. That gives you a positive charge on this carbon down here. This is technically a valid Lewis structure and a valid resonance structure, but this one has 3 charges. That's bordering on way too many charges. So we would call this a very minor contributor. It does exist, but it's a very minor contributor. So we try to not draw things like that. We're concerned about these 2 contributors because they're the major contributors, and then this one is minor. So if you were considering all 3 of these resonance contributors, this is your number 1, winner, winner, chicken dinner. This is absolutely number 2, and this would be number 3. So sometimes students get a little panicked saying, I don't know how to know when I'm finished, when I've drawn enough. Yeah, this one is this number 3 is absolutely not necessary because it's a minor contributor. But sometimes we will draw things like that. We are not ready for the context of why yet, but sometimes we will draw things like that when we're drawing reactions. You'll see. As I said before, organic chemists are pretty obsessed with their arrows of all types. curved arrows, but other arrows too. We get real nitpicky about this being a resonance arrow and this being an equilibrium arrow. It's unfortunately a big deal to us organic chemists, so be careful there. In general, when a molecule can be represented by multiple resonance structures, it's considered more stable. So we talk about the stability of molecules frequently, and if that molecule can be represented by multiple resonance contributors, it's generally more stable. Resonance is a big deal. It will become a bigger and bigger deal as we go on. So I think this is a pretty important slide that you should probably put stars on and boxes around and lots of highlighters on. It's kind of telling you how to begin when you're drawing resonance contributors. Just to make things easier as we refer to them, I'm going to put numbers on these bullet points, not because it's an order of importance whatsoever, but I'm going to put numbers so that when I say, are we in situation number 1, 2, 3, or 5, 4, or 5, this is what I'm referring to. Let's draw some resonance examples. Benzene is one of the most common, most famous examples of resonance. Benzene has pi bonds that can be moved. So if I start by trying to move this pi bond to between those carbons, I need to also move this pi bond because this arrow tells me I'm making a new bond to that carbon. That carbon already has 4 bonds, so you need to move that pi bond also. That would explode that carbon, so you need to move that pi bond. So benzene can be drawn as having the pi bonds here, here, and here, or there, there, and there. Benzene can be drawn either way. Benzene's hybrid should have ... bonds all around, but because that is time consuming to do ... around the 6-membered ring, we really take more shortcuts and we draw a circle in a benzene. What that circle signifies is that we are showing and acknowledging that electrons are distributed equally throughout that whole benzene ring. All of this matters because remember, if you go back to Gen Chem knowledge, a double bond should be shorter than a single bond. So if benzene really had double and single bonds, it should mean that you've got something crazy like this. That's not the greatest ratio, I know, but where all the double bonds are short and the single bonds are long. That's not the way benzene is really observed. Benzene is really observed to have equal length and equal strength bonds between all of its carbon-carbon things. So that's benzene. Let's do the next one. So in general, the rule of resonance is to move the fewest number of electrons possible. Benzene is a little bit different. I mean, we do move the fewest number possible, but that required us to move 6 pi electrons. 3 curved arrows were required there. But if possible, we really only like to move 2 electrons at a time, but sometimes you're required to move 4. Let me show you what I mean. In this molecule, if you go back through our last slide of how do you know when to consider resonance? Do we have an atom with a positive charge and less than an octet in this? No. Do we have an atom with a negative charge and an unshared pair? No. Do we have benzene? Do we have a pi bond between neighboring atoms of different electronegativities? Check, check. That's what we've got. We are in situation number 4 in this molecule. So we have a pi bond between atoms of different electronegativities. That's this carbon-oxygen pi bond. So the way I'm going to move that one is curved arrow goes from the pi bond to the oxygen. Electrons always go toward the more electronegative atom when you're breaking a pi bond like that. That pi bond stays in place. We didn't do anything with it. This double bond becomes a single bond. That oxygen had 2 lone pairs before. And now he's got a 3rd lone pair because that pi bond was broken to give him an extra lone pair. This molecule had no formal charges, but this one has formal charges. Who lost electrons in our transaction? carbon did. Carbon had 4 bonds here, and he's only got 3 bonds there. That carbon is a formal positive. Oxygen had 2 bonds and 2 lone pairs. Now he's got 1 bond and 3 lone pairs. That oxygen is negatively charged. Yeah? Every time you draw a resonance contributor, you must ask yourself, am I finished or can I do more? So from here, if you go back to our how do I know when to consider resonance and say, situation number 1, an atom with a positive charge and less than an octet next to a pi bond or an atom with an unshared pair. Yeah, we have that. This carbon has less than an octet and it's next door to a pi bond. So I'm going to treat this carbon like my hinge, and I'm going to swing electrons that direction. The electrons from this pi bond go that way. So I get this. Pi bond here instead of there. Oxygen up here still has 3 lone pairs and a negative charge. Carbon here now has 4 bonds, and so he now has a full octet. Carbon down here, though, he lost a bond in my transaction. He's got a positive. Remember, there's a hydrogen in the background here that was assumed all along. It's still there now, but that carbon still has a positive charge because he lost that pi bond. So if I drew a compilation of the hybrid, we really won't do this for all molecules, I promise. But if I drew the compilation of the hybrid, it would have dot, dot, dots along all of that stuff. There's a partial negative on the oxygen because in 2 of my structures, oxygen has a negative charge. There's a partial positive on this carbon here because carbon has a partial positive on one of those. There's a partial positive on this carbon down in the corner because of this 3rd resonance structure. Okay, so why does resonance matter? It's our first really tough concept. Students don't love resonance in the beginning, but you'll get better at it. I have faith in you. I believe in you. Why do we draw all this resonance stuff? Well, we're all about reactions. And so if we react something, we're going to say it's an A minus. If we react something that has a negative charge with this molecule, where is that negative molecule going to react? It is definitely going to react either here at that carbon or here at that carbon. It won't react at any of these other carbons that don't have partial positives. It will react this red position number 1 or this red position number 2. That's the only places it's going to go. Conversely, if I added a positively charged thing, if this were not an A minus, but let's say an H plus, where's that H plus going to react? Obviously, it's going to hook up with the oxygen because the oxygen had a negative charge. So right now, we're only focused on resonance, and resonance is tough enough, but we're heading to a point where we're going to draw reactions with molecules, and you have to consider resonance in your head over and over and over again in order to predict the proper products of reactions. Got it? Our last example on this slide, let's do it. If I go backwards to situation number 1, do I have an atom with a positive charge, less than an octet? Nope. Atom with a negative charge, an unshared pair? Nope. Benzene. Yes, I do have benzene, but I also have something else special over here, so I'm going to keep reading. A pi bond between atoms of different electronegativities. An atom with an unshared pair of electrons conjugated with a pi system. First of all, I don't know what that conjugated means. That's where we really are. We're in situation number 5 here. We have an atom with an unshared pair conjugated with a pi system. Nitrogen is my atom with an unshared pair. I'm going to define conjugated. Remind me in a minute. Yes, I know you can't really do that. Remind me in a minute to define conjugated. So this lone pair on nitrogen is conjugated, whatever the heck that means. That means this lone pair can be shared to make a double bond between nitrogen and carbon. This carbon already had 4 bonds, so that's not great to make a new double bond unless we move the double bond that's already there. So I'm making a lone pair into a pi bond. I'm moving a pi bond to become a lone pair. So resonance really likes to move the fewest number of electrons possible. But when I moved only those first two, that would explode that carbon. So I have to move 2 additional electrons. So 4 electrons total are moving in this molecule. Make a new pi bond between nitrogen and carbon, and this pi bond goes away to become a lone pair on that corner carbon. Yep. Carbon with a lone pair, that's a negatively charged carbon. Nitrogen with 4 bonds, that's a positively charged nitrogen. Every time after you draw a resonance contributor, you ask yourself, am I finished or can I do more? So you go back through that list again. Number 1, an atom with a positive charge of less than an octet. Well, we do have an atom with a positive charge, but it has an octet, so we're not there. Question number 2, situation number 2. Atom with a negative charge and an unshared pair next to a pi bond. Atom with a negative charge and an unshared pair, got that, next to a pi bond. Yep, that's where we are. So that electrons from that carbon, that unshared pair, can become a new pi bond, and that new pi bond gets kicked around to the next corner. We don't cascade it all the way around. We're moving as few electrons as possible, and in this example, that's 4 electrons. It is almost always 2 or 4 electrons. Try to not move more than 4 electrons ever, but move 2 if you can possibly just move 2. So we got this thing becoming a double bond. Nitrogen up here keeps the double bond and keeps the positive charge because of that. This carbon down below now has a negative. And we've drawn a new resonance structure. We go back to the drawing board. Am I in situation number 1, 2, 3, 4, or 5? Can I draw any more? Yes, I can. This is also situation number 2. So I can take those lone pairs, share them to make a double, take that double to the corner, lone pair on the corner up there now. Positive on the nitrogen, negative on the carbon. Situation number 1 through 5, where am I? This is also situation number 2, atom with an unshared pair next door to a pi bond. So I draw that to give electrons back to nitrogen. This lone pair is back on nitrogen. And you might look at those things and say, that's exactly where I started. And I say, well, it's really similar, but it's a little bit different from where you actually started. A little bit different. So the pi bonds were here, here, and here. And now they're there, there, and there. Yeah, I did resonance around that benzene, is the take home from between those 2 molecules. So if I drew the hybrid of this thing, the hybrid of this thing would have a dot, 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 like that. The nitrogen will be partially positive, this carbon partially negative, this carbon partially negative, and that carbon partially negative. These carbons never have any charge, those 3 carbons with arrows, they never have any charge in any of my resonance structures. So they do not get a partial positive, they do not get a partial negative, they get nothing. Why does all this resonance matter? Because if I do reactions, in this example, if I did a reaction with a positively charged thing, that positively charged thing would react here, or there. That's why resonance matters. In all of these examples, I have forgotten to explain who's the winner, chicken dinner, which resonance contributor contributes most or equally or whatever. In Lewis structures, we want to avoid formal charges if possible. So this beginning molecule and this ending molecule have no formal charges, and everybody has an octet in them. So we would say these 2 are equal contributors, and those 2 equal contributors are more important than these 3 that have charges. So among these 5 resonance contributors, 2 of them contribute most and are equal, and then actually the other 3 would be equivalent contributors as well. but not as important as the pink circled ones. If we go back to our previous example, it's a similar decision. This one has no formal charges and everybody has an octet. So this one is the winner, winner, chicken dinner, the most important resonance contributor. The hybrid molecule really looks most like the pink circled one. So then you might say, why do we draw resonance in the beginning? Why do we draw resonance in the first place? Well, as I described before, it's all about reactions and where reactions take place. If we go back to benzene, benzene had 2 resonance contributors. They are equal resonance contributors.